Okay, that's been good morning again. Thank you for joining me as always. And this week we start chapter 5, as you probably noticed, and I saw a few posts on the discussion board. That's good that you did start working on lesson 9. That means what I will do, I will introduce chapter 5, and we do have 4 sections. That's what it is. In chapter 5, we will actually start the second part of calculus, which is not differential, integral calculus. Okay? That's what we will do. We will kind of like trying to get back. Having a derivative, having a rate of change, we will try to recover an original function. Like, for example, the first section, 5.1, is focused on the distance and velocity. That means having a velocity, a speed, we can try to recover a distance function. Yeah? Because the velocity, the speed, is the rate of change of the distance with respect to time. That means having a rate, again, we will try to get a distance. For example, okay? That means from the derivative, we will trying to get back to the original function. And this process we call integration. Yeah? That means integration is something like an inverse to differentiation. Okay? That means let's start. I will switch off the video, then it's better. And okay, I'm here. Okay, that means just what I said. Having a velocity, we will try to get the distance. And how can we do this? To say really, really broadly, if we will have a distance, I mean the velocity function, let's look at this graph, the velocity function, the area under the curve of the velocity will represent the distance. Okay? That means having a velocity and computing the area under the curve and below the x-axis, of course, we will be able to find the distance traveled, estimate the distance. Okay? That means always the area under the curve. That's how we can, as I said, recover an original function having a rate of change. And we do have some process, we do have some methods to estimate that area, because we can see it's not easy to find the area if one of the sides is curved. The x-axis is fine, it's the straight line, the vertical lines, the 0 and 10, I'm just looking at the area between 0 and 10, it's straight, but the top, of course, the velocity, it's not a straight line, yeah, it's the curve. That means we will have a few ways to get that estimation, and you can probably see we are building like a rectangles. That's mean taking the area of the rectangles, we can find the sum of it, and that will be our estimate. We have a few ways to get these rectangles, because you can see we can have the lower one or we can have the higher one, okay? Which we call like the left hand side and the right hand side. You probably noticed when you were studying for this chapter. And also, I can switch. In order to get better approximation, we may increase number of rectangles. Okay? That means the whole point for this chapter will be to find the area under the curve. Right? Because that's I can say the integration process. The integral of the function means the area under the curve. We do have some details to add, which I will add in a minute, but that's the general definition. Yes? The integration, the integral of the function is the area. And we will try to estimate. And you can probably notice that if we will choose a bigger number of rectangles, then the estimation is better, because we nicely cover the entire area under the curve. Let's look at the first graph. We have 1, 2, 3, 4, 5 rectangles, but we not really, like, we do have some empty, we do have some areas that we're not really using, which the approximation is not as good as, for example, if I will pick 20 of them, or even 200, right? I can even pick 200, 2000. And of course, the better approximation is if n is infinitely, like if we have infinitely many of these rectangles. Okay, but that will be, we will add this. Then it's perfect. You can imagine like really, really slim rectangles and like adding all of the areas together. Okay, and delta t, you can see delta t is just like the delta t is the base, the width of this rectangle. That means if we had an interval from 0 to 20, having 5 of these rectangles, I will divide the distance, the whole interval. I can write a little bit nicer. The 20 I can divide by number of rectangles, and of course I can get my delta t, because the t is on the x-axis. That means this is the base of the rectangle. And we can see this one from 0 to 20 is divided by 10, which is 2. Okay, and I can, and for this one, of course, is 20. That means 20 divided by 20, it's 1. That means we will go by 1 and we will create a rectangle. Okay? I mean, first of all, we're just creating like a strips, like a stripes. Okay? And then we're trying to get the top of the rectangle. And we will try to get how, to the procedure. Okay? But we know how we can approximate the area under the curve, taking rectangles. And now this is the formula. That means what we can have. We have a curve, okay? And the point is to find the area under the curve. That means we will divide, one more time, I will divide my sub-interval from A to B, that's my A, okay, to B, and we can pick how many rectangles. Okay. But let's say, I know that we have like almost infinitely many here. The picture doesn't really show, but let's say we have 1, 2, 3, 4. That means I will divide the entire sub-interval from A to B by 4. Then I will get my delta t. Okay, B minus A, that's the length between A and B, and divide by number of rectangles. That's we know how to get the base. Now, we do have to find the height of these rectangles, right? That's mean what I can do. Let's look at this. Let's look at this sub-interval. Okay? I do have like t sub 0 and let's say t sub 1. And I will have t sub 2 and let's say t sub 3 for now. And of course t sub 4. Okay, we do have just 4. I will skip the infinitely many terms from now. Okay, that's me looking at the first sub-interval between t sub 0 and t sub 1. Okay, I can actually see left and the right-hand side endpoint. That means t sub 0 is on the left-hand side and t sub 1 is on the right-hand side. That means I can pick one of them, and this actually picture represents the left. That means one more time. T sub 0, T sub 1. T sub 0 is on the left. That means I'm picking this value and trying to find the corresponding value of the function. And this will give me the height. Okay, that's done. That means I do have my first rectangle. Now, looking at a second sub-interval, which this will be second, T sub 1, T sub 2. Now, I have to be consistent and I follow my left-hand side sum. I know that T sub 1 is on the left-hand side, right? Looking at this sub-interval, that's my second sub-interval. That means the second one is telling me that T sub 1 is on the left-hand side. Then I'm trying to go by this, and that's the corresponding value, and this will give me the height. Okay, and then I will follow the same rule. T sub 2 is on the left-hand side. T sub 2 has corresponding value here, and horizontal line will give me the value. And then T sub 3 is on the left-hand side. This will give me height. Right? That we can see. All of the height of these rectangles corresponds to the value which was related to the left-hand side endpoint of the subinterval. Okay? And then I can find, now I know the height, because the height will be the value. We can see, like, for example, the area of the first one, of the first rectangle will be delta t, which is the base times height, and height will be the value of the function for t sub 0. Then the second, I can remove this. This is the first rectangle, second rectangle, third one, and fourth one. The second will be base times the height, but height is the green line, actually, which is the value of the function for t sub 1, and so on. And then I can add all of them together to have my estimate. And we can, yes, we can see this, that I can have infinitely many of them, which then it's, yeah, then it's better approximation. But we have to understand the idea. That's the reason that I use only 4. Now, let's look at this one. This is the same thing, but we use the right-hand side. Right? That means, again, I can have t from A to B. Let's say t sub 0, t sub 1, t sub 3, and t sub 4. And I do have my stripes. I can do this. Now I have to create a rectangles, but I want to use the right-hand side endpoints. That means now I can use different color, green. T sub 0, T sub 1. T sub 1 is on the right-hand side. That means this will give me the height. And that's the height. Now, T sub 1, T sub 2. T sub 2 is on the right-hand side. This will give me the height. And respectively, T sub 3 is on the right-hand side, and T sub 4. Okay? That means that's how we can find. And the same thing. The area of the rectangle is base times height. But now the first one, the area of the first one will be base, which is delta t, times the value of the function for t sub 1. That means, please notice, t sub 1, t sub 0. Because t sub 0 was on the left. This one is on the right. Okay? And that's will be the good estimate. Okay? That we know how to compute this. Let's put this in action. That means I do have a first question. Let's try to estimate, because again, this is just the introduction to the integral calculus, and everything will be like kind of like estimation, approximation. Okay? And you probably know that we will get some proper tools, systematic tools, that we will get exact value. Okay? Because we do have a proper integration method, but at the moment it's just the estimation. Okay, that's what we have. The figure shows the velocity of a runner from between 0 and 15, which is time. Let's say between 0 and 15 minutes. And the rectangles used to estimate the distance traveled. That we can see. If the velocity is provided, the area under the curve will give me back my original function, which is distance. Because we remember, having a distance and taking the derivative, we will get the velocity. But now it's the other way. Having a velocity function, that's the blue curve, and then estimating the area under the curve, below the x-axis, will give me distance. Okay, that means let's answer all of these questions. Do the rectangles represent the left or the right sum? What do you think? These rectangles, the blue columns, represents the left or the right-hand side? It's the right-hand side, right? Because we do have, this goes by 3, 6, 9, 12, 15. And we can see I have my sub-interval between 0 and 3, and I believe 3 is giving me height. Yes, that means that's the right-hand side. And then again, 6 is giving me height. We can see not 3. 3 is giving me on this one. Okay, and respectively 9 and 12 and 15. That means I do have, definitely I can say the right hand side sum or the endpoints. Okay, that means I can actually answer here, right hand side. Okay, do the rectangles lead to an upper or lower estimation? Oh yes, because I didn't mention that. Let me come back here. We can see sometimes if, of course, it's like common sense, if the rectangles are sticking out, and taking the areas of all of them, we will definitely like overestimate, right? Because theoretically we don't need that part. That's our tool, that's the estimation, but this will give me overestimation. This actually is giving me underestimation because I'm missing a few pieces. Okay? But now, what do you think? The right-hand side, if I will get the areas of all of these rectangles, am I gonna under or lower? I will under or overestimate? Of course, under, because we can see the white, we can see the missing part. That means this will give me a lower estimate. Okay, good. Now, what is the value of n? Who can give me the value of n? N is just simply number of rectangles or number of sub-intervals. Yeah. How many rectangles we have? How many columns I have? Thank you, Craig, for answering my questions. I know they are quite obvious, but always remember the easiest questions are the hardest to answer. Okay, that we do have 5 of them. Who can tell me what's the value of delta t? What is delta t? Delta t is the base of this rectangle, or I can say the width of the sub-interval. That means what we have? Or it is free, of course, because we can nicely see, or maybe I can write here, this distance is delta t and it is free because we go by free. Or I can think that I have my interval between 0 and 15, 15 minus 0, and I have n. Let me actually put n is 5. I can put, because to find the length of the entire distance between a and b, we have to subtract b minus a. Okay, and then we can nicely see it is free. We go by free. Again, common, like we can see. Okay, that means now let's estimate. What I will do, I will probably simply, because since I have the nice like grid, I will simply count the number, count the all of the squares. I mean all of the rectangles. I can go by rectangles. I can try to get that area plus this one, plus this one, plus this one, and plus this one. But I don't really have the formula for the function, for the velocity. That means I will just count the rectangles. That means, let's see, the easiest way is to do this. How many rectangles we have? 1, 2, I mean the small one. Okay, the small one. I'm not saying about the big one, the columns. I'm just trying to find this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and maybe they all, this is missing a little bit, but let's say 13 together with this one, maybe 13 and a half. But again, it's really the approximation. Yeah, if we will miss a few decimal points, that's fine. Okay, that means the whole, yes, the whole distance, because that's the distance. Yes, we shouldn't forget what we're actually calculating. The whole distance traveled, okay, will be, we have 13, and the base, oh, that color will be not visible. The base is 3. That means 13 times 3. And the height, oh, what is the height of the small rectangle? It goes by 4, 8, 12. Okay, times 4. 13 times 3 times 4. Oh, 13 times 12. I think it's 156. If that's, yeah, because it's 12 times 12 is 144 plus another 12. Yes, it's correct. Okay. Okay. That we do have 156, whatever like was the, I don't know, kilometers. Yeah. Yeah. That means that's the unit. That's how we can, because we know distance is just in we know the units for distance. Okay, 156, and I can say just units. Yeah, distance units. Okay, but we can see this is important to just know how we did estimate. And you can see I did count each part. Okay, let's try to get another one. With time t in seconds, the velocity of a bicycle in feet per second, of course, the speed, is given by the formula 5t. How far does the bicycle travel in 3 seconds? Okay, excellent, because we like the function. It's the linear function. That means my rate of change of the distance with respect to time is defined as a 5t. Really nice function. This will be the velocity, and that's the time. 5 is simply a straight line, or maybe I shouldn't draw the negative. It's just a straight line with the slope 5. That means this is my velocity 5t. I like to have the formula, first of all, and this is just a straight line. And then from 0 to 3. Okay, let me put a little bit longer. Okay. And that means this is the velocity. The distance traveled will be simply the area under the curve. Okay, that means how far the bicycle travels in 3 seconds. With the velocity is the linear, that means the distance traveled is just the area. And that area, let me put again, distance traveled is the area, okay? And this one, that area. And who can tell me how can I compute that area? What is the shape? Yeah, the area, of course, under the velocity and above the x-axis. That we can nicely see is the triangle. Do you remember the area of the triangle? How can we compute? Because the region is the triangle. We can nicely compute. We remember 1/2 base times height, okay, because it's the triangle. Okay, triangle. And then 1/2 base, of course, that's the base of the triangle, because now we don't even have to like divide, we don't have to use any approximation. This will be perfect, this will be exact value. The base is 3, and who can tell me height? This is height. Who can tell me that value? This will be height. Do you think you can give me the height of the rectangle, of the triangle? Oh, no? What's the corresponding value of the function for 3? Of course, 15. I know. It's 15 because it's 5 times 3. That means the height is 15. Okay, that means what we have? We do have 15 times 3, it's 45 divided by 2, 22.5. And what units? Because the velocity was feet per second, right? But we know that always if we integrating, I can use this, we will take the rate and multiply by the time. Okay, that's my rate, and multiply by the time. That means this will be the distance. Oh? Can you hear me? I think so, because I've got the message on the screen that you can't hear me. No, you can hear me, good. Okay, That means distance, it's feet. We don't even have to think about, let me just cancel that message. We don't even have to like really think about canceling like the units, because of course the common sense is we know the distance is in that. It's not like the seconds, minutes. It's of course it's feet. Okay, but make sure that you know what I did. Okay? Just the area of this. Okay, let's keep working. That's we can see how we can. I'm just giving you different examples, like how to get the area under the curve. Okay, now we have a table. Probably the same thing, but using the values from the table. Okay, a car comes to the stop 6 seconds after the driver applies the brakes. While the brakes are on, the velocities recorded are in, and then we do have some data. Okay? Time since brakes applied, that means at 0 seconds, the velocity was 88 feet per second. 2 seconds, after 2 seconds, 45, 4 seconds, 16, and of course, 6 seconds, 0. Yeah, the car stops. Give lower and upper estimate for the distance the car traveled after the brakes were applied. Okay, that we have to estimate. On a sketch of the velocity against time, show the lower and upper estimate of part A. Okay, that's what we can do. We don't have to, because we can see the values in the table, but I think will be helpful to maybe put them on the graph. That means at 0, this will be velocity. Because I don't have a graph, I don't have a formula, but I have a data. But from the data, I can still get something. Okay, for 0, the velocity was 88. Okay, and then at 2, I can, how can I? Okay, I can maybe draw something like that. It's gonna be good. 4, oh no, I need, oh, am I destroying everything? Okay, let's just do, because I want to have nice, okay. 2, why I think 8? You see, I'm just trying to divide this equally. Please do not laugh. Okay, that's 6, 0. And then, okay, we don't have, I'm trying to divide like that. 2, 4, 6. Good. This value is, the value after 2 seconds is 45. After 4 seconds is 16 and 0. Okay, now it's better. Okay, that we can see I can actually divide like that, because then I have my stripes. Okay, and we can see if I will pick, let's start, we can start with any, but let's start with the left hand side. Okay, that means the left hand side. I can use maybe the green color. 0 and 2. 0 is on the left. That means 0, the value for 0 will give me the height. Yeah, you can see that's how I can compute. Now, looking at the sub-interval between 2 and 4, 2 is on the left-hand side. That means 2 will give me the height, the value for 2. And then the value for 4 will give me the height. That we can see the left-hand side will give me, what do you think, lower estimate or upper estimate? Can you tell me? I know that you know. It's upper, because we can see the rectangles are a little bit too big. They sticking out, like, because I need, in order to get that distance, okay, we really have to get the area under the curve, but they are a little bit above. That means this will be upper estimate. Okay, and just simply the area. We do have the first rectangle, it's we can actually see the delta t is 2 because we're changing the time by 2. 2 seconds, 4 seconds, 6 seconds. Okay? That means delta 2. And that means we do have 2 times the value, okay, for value of the function. Maybe I can write this for you at 0. And then 2 times value of the velocity at 2, and 2 times the value of the velocity at 4. Value of the velocity at 0 is 88. Value the velocity at 2 seconds is, you can watch me what I'm doing, 45. And then for 4 is 16. Okay, this will be 160, 176 plus 90 plus 32. And I believe this will give me 298. And of course, distance, feet. You can check, but I think I am 6 is 2, 8. I think it's correct, okay? That we can see how we can get the one of the estimate, upper. Now let's try to use the right-hand side, okay? Which the right-hand side, of course, must be the lower, but let's see. 0 and 2. 2 is on the right-hand side. That means 2 will give me the height, the value for 2. Or maybe I should use the other way. 2 and 4. 4 is on the right-hand side. That means 4 will give me the height. And 4 and 6. 6 is on the right-hand side. And actually, 6 has the value 0. No rectangle. But I can still use it in my calculation. That means this is definitely lower estimate. And what we have? We have 2, which is delta t, times the value of the function, not f, v, at 2, plus 2, and then value of the function at 4, and times 2 base, and value of the function at 6, which is 0. Value of the function, velocity at 2 is 45, and then at 4 is 16, and at 6 is 0. Okay, 90 plus 32 and plus 0, 122 feet. Okay. That means the estimate, of course, is between. We can see it's a huge difference, 298 and 122, because we can see how big are they. And the data are not really like, we do have only 3 rectangles. If I will have like the data like every I don't know, like this is in seconds, let's say milliseconds, yes, then I will have much more rectangles and the approximation will be good. But at least, yeah, we got some numbers, at least. Okay. That make sure that we know how to recognize upper estimate, the lower estimate, and of course, left-hand side and the right-hand side rectangles. But please note, not always the left-hand side will give me upper estimate. Sometimes could be the other way. Okay. Okay. And then I do have, okay, I have the same question, but I have the solution for you. That means you can check. It's the same thing. I mean, we do have some solution, but we can try to quickly get the answer. Figure shows the velocity. That means this graph is the velocity v of an object in meters per second. Estimate the total distance the objects traveled between 0 and 6. Okay? That means the total distance, again, it's the area under the curve. That means let's just count the small rectangles. We don't have to be worried for the delta t values left and the right. Just simply get, simply we have to estimate that area. Okay, but I will remove this and let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Of course, I did count the nice full squares. I mean, they are rectangles. Okay, that we do have 11, and then I think I can say 12, including this. I can say 13, including this, and maybe 14 including this, and I don't know, half, right? This will be like a half. That's when we do have 14 and a half. 14 and a half, and then each of them, the base is 1, and the height is actually 10. Oh, nice calculation. Okay, that means that distance, the total distance traveled will be this, between 0 and 6, of course. That means 14.5 times 10, it's 145, and just distance, meters. Okay. As we can see, I did and if you can, I type the solution for you, and it says between 140 and 150. Perfect, we got 145, because I kind of count this as a half. But we can see, again, the approximation. Yeah? We have to have this like intuitive understanding. Okay, that's everything for section 5.1. Now, a definite integral. I kind of use this terminology, but whatever we did at the moment, we did like calculate. I can even come back. Yeah? I did estimate, I did calculate the area under the curve. That's between 0 and 6. And I can tell you this number, the new terminology, the new definition, this will be a definite integral. Let's see. Okay. We do have, of course, a special notation. Okay. That means the notation for the integral, it's like a kind of like elongated S. Okay, because actually what this means the summation of all of these rectangles. Yeah, that's what actually this means. And then we do have a limit of integration from A to B. Okay? And what we're doing, we're integrating a certain function. And we always have to say that we're integrating with respect to the variable t. That means we will always have something like dt, dx, depends what we're integrating with. But arithmetically, algebraically, this doesn't really have a meaning. Okay, you can probably notice, because we don't really go really deeply in the definition, but this is the definite integral. Okay, that's the symbol, that's the notation, but this is a definition. Okay, that means definite integral represents the like the limit, which means the behavior at infinity of this. And this is nothing else like the summation of the areas of all of these rectangles. Okay, that means if I can, I don't know if I have enough room, but if I have my function, and if I will integrate the function f of x between A and B, yes, I will make my stripes, and then I will use the left or the right hand side, create the rectangles and add them together. That means adding together, of course, sigma is telling me that I am adding them. And each of them has the area, the base, which this is the base, and that's the height. Right? That's the base. Delta t will give me the base of the rectangle, and the value of the function for the corresponding points, of course, left or right, will give me the height. Base times the height. This is just the area of the rectangle. Adding all of them together and having a perfect approximation, I need infinitely many of them. That we can see. This is simply the area under the curve and the perfect approximation. Because not like just having one or two of them, three of them, no, infinitely many of them. And then instead of like always writing a sigma and height, time base, and infinitely many of them, we do have the nice short notation. This is a definite integral from A to B, and we're integrating the function f of t. I can put t. Okay. And dt with respect to t, of course. And yes, if we do not have the infinitely many of them, we have like 5, 6, or 7 of them, we will have just the approximation. But if it's infinitely many of them, it's a perfect value, and of course the definite integral is telling me this. Okay, and we do have a special name. This summation we call a Riemann sum. Riemann is just the name of the German mathematician, and he, of course, discovered, developed the formulas and the idea, the concept. In the limit of the Riemann sum, it's simply a definite integral. Okay? And the function that we're integrating, we call integrand. Okay? Integrand. And A and B are the limits of integration. And that means this slide is like kind of telling me the like the new words, new terminology. Okay, but technically, like practically, whatever we will do, we will probably do everything what we did in section 5.1. Because in order to estimate a definite integral, we have to estimate the area under the curve. Okay. And this is just an example. That's another one. We did this. The only thing is I'm using the new notation. Okay? That means now I will not say, oh, estimate the total distance if this is velocity, or estimate the area under the curve. I will say, estimate this, an integral from 0 to 6 of f of x dx. Yeah, that's, we have to understand this. This means that's my function f of x between 0 and 6. Okay? And then we know what to do. We can we do have some information. Okay, that means now they're telling us what to do. They want to use left and the right hand sum, and n must be 3. That means the distance from 0 to 6, I have to divide only by 3, 2 and 4, okay? Which actually we can see below. That means it's not gonna be perfect approximation, okay? Because if they will ask me to divide by 6, will be a little bit better, but okay, by 3. Then delta x, of course, is 2 units, right? That means now this is actually, can you tell me this side, it's the left or the right hand side endpoints? Did we use the right or the left hand side on this picture? It's the left, right? Because we can see the left gave me the height. And of course, on this one is the right endpoints. And we can get we do have the formula, all of the values and the numbers, the final answer. But we can see that's the same thing. And kind of like approximating this, we adding the left and the right hand side together, and we're just taking the average. Okay? But the only difference in this section is the new notation. Okay? Everything else is the same. Okay, that's me now. Okay, we can see almost the same question like from the previous section. But instead of saying in the application way, using the application words, we're just using the symbols. Use the figure to estimate an integral from 0 to 20 f of x dx. Okay, well, we can simply see that the integral, we have to remember the integral of the function f of x, the definite integral from 0 to 20, represents the area under the curve. Okay, that's it. Okay, that's me, just this area. Okay, let's count. Yeah, I think that's the easiest way. What I can do? Let me do this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and this is 12, and maybe this one and this part will be 13. What I have? 13. Maybe this one will be 14, but I can add this part. And maybe this one will be 15, right? 15, and this is half of this. That means I did create all of them. Okay, 15. That means this integral will be equal to 15. times and to base times height. Base is 4 and height is just 1. Excellent. Okay, 15 times 4, I think it's 60. And that's 1. Okay. That we can just simply use, if we have the nice, great, we can use just simply all of these, the small rectangles, okay, to compute all of them. Okay, 60. Yeah, but we can see the same thing. And the same thing from the graph. Use the table to estimate the integral, the definite integral from 0 to 40, f of x dx. The values of n and delta x. What values of n and delta x did you use? Okay, do you see what is delta x from the table? What's the delta x? Like how many units we jump from one x to another? That's what the data is. 10. Yes, thank you. Yeah, that means delta x is definitely 10. And again, we don't have to, but maybe for 0 is, that means function is definitely increasing. That means I should start maybe here. For 0, we do have that value. Let me do nicely for 10, 20, 30, and 40. It's not a straight line, but let's do this. For 10, the value is 410, 435, for 30, and for 40. 450 and 460. That's the function f of x, and that's x. Okay. But we can definitely see the delta x is 10. And what do you think? What is n? How many of these sub-intervals we have? Yeah, you can 1, 2, 3, 4. We only have 4. We always have, okay, because I can see we do have 5 values, right? 1, 2, 3, 4, 5. But one of them is only like the end point, like a starting point, initial point. That means I'm not really counting. Yes, that means I will always have one more. That means this is 4, because we can nicely see 1, 2, 3, 4. Okay. Okay. Oh wow, lots of calculation. But let's see. I did use the calculator, but I still want you to get the values. That's what we can do. We can use the left-hand side first. Okay, left-hand side estimate, or left-hand side sum. And I will use maybe green. That means left-hand side 0 is on the left-hand side. That means 350 will give me the height. And then 10, 20, 10 is on the left-hand side. This will be the rectangle. Okay, 20 is on the left-hand side if I look at the third sub-interval. And between 30 and 40, 30 is on the left-hand side. Okay, that means simply the left-hand side sum will be the areas of all of these rectangles. Let me use the same color. Left-hand side sum. Okay, delta x is 10. That means I have 10 times value for 0. 10 times value for 10. 10 times value for 20. And 10 times value for 30, which is this. Okay. But make sure that we understand, because that we can see, that's the height. That's the height, 410, 435, 450. And I did use the calculator. This will be 16,450. Okay? But of course, the final number, it is important, but I really want you to understand this. Okay, and now let's use the right-hand side sum. Okay, between 0, oh, no, too fast. Between 0 and 10, 10 is on the right-hand side. That means 10 will give me the new height. I will have this rectangle. Between 10 and 20, 20 is on the right-hand side. And this will give me the height. Between 20 and 30, 30 is on the right-hand side. Okay, and 30 and 40, 40 is on the right-hand side. This will be my rectangle. That we can see the blue one, the right-hand side, are definitely overestimation. Okay, that means let's see. 10 times the value for 10, which is 410. 10 times the value for 20, which is 435. 10, which is delta x, the base, times the value for 30, which is 450. And the last one, the blue one, is the value for 40, which is 460. And I use the calculator, 17,550. Not bad, because it's we can see it's still the difference. And if we would like to really estimate our integral, the definite integral from 0 to 40 of the function f of x with respect to x, maybe that's too much, we can say approximation, I can possibly add them together and divide by 2. Okay, I can divide them by 2 because that's the only tool at the moment that I have, and it's exactly 17,000. Oh no, why I am pressing the wrong buttons? 17,000. Okay, and we do have the n and the delta x. Okay? That's mean I hope you understand this. You don't have to be, you can maybe get the values right away, but I think the graph is helpful. The graph, when you plot the points and like put the curve, the graph is quite helpful to estimate the values. Okay, that means, as I said, section 5.2 is almost the same like 5.1, but we do have this nice notation of the definite integral. Now, section 5.3 is the same thing, a definite integral, but we will more focus as we will define the definite integral as an area, which we, of course, we did. We're still talking about the areas, but we will have one extra thing to add. That means we know that the definite integral from a to b, f of x dx, is the area under the graph of f between a and b. And everything is fine, and we probably understand if f of x is positive, right? Because we probably didn't realize, but all of my functions were above the x-axis, something like this one. Function, positive, the whole graph is above the x-axis between a and b. And then we can say, yes, that's the area under the curve, and that's the definite integral. Depends which words we can use. But what we may have something like, which one? Maybe let's look at this graph. We may have the situation that part of the function is actually below the x-axis. Yeah, you can see this graph. That means that's my function, f of x, and between 0 and 5. Okay? That means what we have, we will still think in terms of the areas, but I don't know, I think I didn't type. The proper way to say that the definite integral is the same thing, definite integral could be, it is still the area, but we will call the net area. This is the more proper word. And what this means, we can read this, if everything is above the x-axis, that's what we just did, above the x-axis, then all of our values will be positive. Makes sense, because behind this symbol, we do have a definition, and definition is simply the value of the function Like we always get the height of this rectangles is the value of the function. If the value of the function is positive, everything is positive. This makes sense. We will apply the same definition, the same procedure for the areas below the x-axis. And since the value of the function is involved, okay, the value for the sample points, then everything will be simply negative. Okay? That means everything what is placed below the x-axis has the negative values. That means we will think the same way. It's kind of like the area, okay? But we have to think that this is negative. Okay? That means, can you tell me what, looking at this picture, actually that's maybe, can we compute an integral from 0 to 5 of f of x dx? We can see that area is 10, this one is 3. That means what is the total? What will be the total of this integration? It's 7. That means everything what is above positive, everything what is below negative, which of course we subtracting. It is 7. Okay, that means for this one will be everything what is above positive, negative, below negative. That means it is 7. Can you tell me the value of this integral for the graph A? What is this integral? From 0 to 5, the same integral, f of x dx. Now we can see everything it's above. The area is 8. It's simply, yes, thank you, Craig, thank you. It's just 8. And can you, I will just make some. And what about the middle one? The integral from 0 to 5 of the function f of x dx. For the middle one. Can you tell me the answer of this integral? Who can tell me? Everything is below. That means what is the answer? It's actually -6. Thank you. That means this is the, that's what we would like to make sure that we understand. Definite integral still represents the areas. But one more time, I will repeat, since the real values of the functions are involved, if everything is above will be positive, if everything is below, it's negative. Okay? That is the same idea, like we kind of like approximate. We can see the, if I have to compute exactly the area, oh, I will say 6. Yes, but if I would like to compute the integral, we're thinking in terms of the net area. Below means the real values, -6. Okay? Let's make sure that we understand this. Okay, and then what we have? We may also have a question like to find the area between two curves. Okay? But that's a little bit different because this is not just integration. This is actually the application of the integrals. That means to finding the area between two curves, we will always subtract. Yes, we can see the formula. We will subtract the higher function, the function which is about the higher values, minus the lower one. We can see f of x minus g of x. And I can tell you this, it's always positive. Because it's not really just integration. It's like some special formula. Okay? The top function minus the lower. Because you can think, if we will subtract the higher value minus the lower value, we will always get a positive number, right? Like let's say, I don't know, 12 minus 2, 10. If one value, if the first value is greater than the second one, and we're subtracting, always the answer is positive. And I can draw for you, because this is always, that's what confuses us. If we have a function, an x, and let's say I have one, oh, actually, let's say just y. Maybe something like that. And I would like to find the area between A and B. Okay. And this is one function, let's say f of x and g of x. And I would like to find the area between two curves. That means what I will do, I will set up exactly the same integral, the top values, okay, minus the bottom one. And even this one, I will still get the positive number. Yeah, I hope we understand this. And let's even check. Let's say this value is, I don't know, -2. Okay, that's the numbers. Of course, we still thinking about the whole process, but let's just think about the numbers. And let's say this is -10. If I will subtract -2, which is the higher value, minus the lower one, do you think this number is positive? -2 minus -10? Negative and negative is positive. And of course, this is 8 positive. That means that's what I would like to show you, that even if everything is placed below the x-axis, we will still have positive answer if we're looking for the area between two curves. Because this subtraction always gives me positive number. Okay? Even for the integration. Actually, I can keep this because I like you to see -2 plus 10, it's positive 8. Of course, this is just the numerical explanation. We know what the integration means, but just telling you. But let me come back to this one. If we have just integral, of course it's negative. Yeah, because we can see this is just f of x. I'm not subtracting, I'm not adding anything. It's just simply integral. Then it's negative. Okay. Now let's look at a few examples. Oh, okay, we shouldn't see the solutions, but that's okay. For each of the functions graphed in the figure below, decide whether the given integral is positive, negative, or maybe approximately 0. Okay, that means, what do you think? Is this integral, oh, we do have a little bit here. That means between 0 and 5. We have a little bit here and here. Do you think this integral for the part A is positive or negative? Who can tell me this? This is just integral. No application, no areas. Of course, it's negative. Of course. What about this one? Between 0 and 5. This one and this part. From 0 to 5, the integration of f of x with respect to x. Do you think this one is positive or negative? It's positive because more areas, more region is above. And what about this one? Between 0 and 5, that part and this one. The integral from 0 to 5 of the function f of x dx. What do you think? Is this one positive, negative, or maybe 0? I can maybe remove my amount of the red color is, I think it's 0. I mean, we can say, yeah, I can say equal. I think this part is exactly, the positive part is exactly the same like negative. Yeah, that we can see, we can even have a negative values. I was gonna say 0. We can even have a 0. But again, this is just an integral, definitely integral. Okay? Shall we do this one? Or maybe, because this is the same thing, let's maybe do this. Use the figure to find the following values of the integral from the values of, and then we have the integrals from a to b, from b to c, from a to c, from, oh, we can skip the absolute value for now, because everything, we don't have to, everything will be positive. Okay, that's what is the value of the integral from a to b looking at this function f of x. That's f of x. Can you tell me the answer for a, b, and c? That means from a to b, it's 13. Excellent. What about from b to c? Who can tell me from b to c? It's Inger. It's from b to c. Yes, it's actually below. It's below everything, because we're not looking at the areas at the moment, the actual areas. Yeah, we're just looking for the definite integral. Okay, What about the integral from a to c? Who can tell me that? Of course, is this. 11. Good, really good. And yes, from a to c, absolute value, yeah, we have, of course, yes, because we have to think that this is actually respectively the mirror image above. That means this will be actually positive too. 13 plus 2, of course, correct, yes, 15. Because every absolute value of negative numbers are the same thing but positive. And that we can think. But okay, I will keep this because I don't wanna confuse you. Okay, and then I have another one, but I can skip this, is the same thing. And then what I have one question that somebody asked on the discussion board. I think it's from section 5.3, and it's number 3. And also number 5. Yes, okay. Okay, but again, this question, we still don't have enough tools, but let's see. I did graph this because what is this asking me? This is asking me find the total area. That means now we can see. We're not only integrating, we're using the integrals as a, like, this is the application. The total area between the function 4 minus x squared, which is upside down parabola, okay, with the 4 units up, and the x-axis. Okay, between 0 and 3, that's mean, okay, the total area between the curve, this one, and the x-axis, that means this is the x-axis. Yeah? Let's do the proper settings. I don't know if we can nicely get the value, but we will try. And between 0 and 3, okay, between 0 and 3. Okay, that's we do have that region. Okay, and we will have that region. Because I just want to make the settings correctly. And what we can see, because we remember the total area, it's always an integral from a to b, and I have to find the top function minus the bottom function. I mean the total area between two curves. Okay, that means f and g, and then everything with respect to x. As we can see, we always have this difference, and we always get positive number. And we can definitely see that this parabola, okay, and the x-axis, they have point of the intersection, which I think it's 2. And this point of the intersection are changing the position of the function. Let's say this is f, and the x-axis will be g, f of x, g of x. Because on the interval from 0 to 2, parabola, okay, parabola, which is f, we call parabola f of x. It's the top function. And g of x, it's the x-axis. The x-axis has the formula y equals to 0 because it's a constant function 0. Value is 0. I can actually put these values. That means my f of x function, it's parabola minus 0. Of course, it's funny to put minus 0, but I really want to follow my definition. Yeah, because it's the top value minus the lower value. We can see the top function, parabola minus 0. Okay? And then, of course, we have to, at the moment, we have to just estimate. Yeah, like I can count maybe number of the squares, but let's just leave it. Maybe we can do it. But this for me is the important thing. That means this is the first one. Okay. And now let's try to find the integral, just to define the integral for the second part. Now we can see between 2 and 3, actually the x-axis are the function with the highest value. That means 0, it's my g of x, this is g of x, and f of x is below. That's we definitely switching the order. F of x will be parabola, and we have to subtract. And of course, we have to like estimate. We can count, you know how to estimate. But this is for me the most important part. We have to make sure that we have this point of the intersection, and we know which function is on the top, which function is on the bottom. And I can tell you this, a sub a, that area will be positive, and even this one will be also positive. Because of that, you can see we integrating function f of x, and normally the integral will be negative. Having this extra negative will give me positive. But of course, I am focusing on my formula for the total area between two points. And let's just leave it, because then I have to probably remove and I have to count these rectangles, I mean squares. But no, we will, because in the second part of this chapter, we will definitely learn quickly how to get these values. But make sure that you have these. Okay, and I think, let me check. Yeah, this is also quadratic, but let's get at least the settings. I don't have the graph, we can maybe get it. Find the total area between x squared and 3x. That means now what we have, x squared looks like that. Yes, we know the parent function. A little bit too wide. I mean, that's parabola. And 3x is just the straight line, okay, with the slope 3. But would be nice to have that point. And this is that area. This one looks nice because this is I can call f of x 3x, and the bottom one I can call x squared. That makes sense. And what we need a point, or points, I think looks like one, of intersection. Function x squared, the same like 3x. Let's subtract 3x from both sides. Let's factor out x. And we can see that zero product property is giving me 0 or 3. That means 0, and this is 3. Makes sense. And now I can just set up nicely an integral. The total area will be a definite integral from 0 to 3, and the top function minus the bottom one. That we can see how important it is to know which one is the top one, which one is the bottom one, not the other way. And this is, again, I'm not gonna estimate at the moment. Probably if I will draw it and if I will have my grid, I can estimate, but we definitely know, is this answer gonna be positive or negative? Who can tell me this? Positive or negative? Oh, I'm sure you hear. It's, yeah, always positive. Yes, thank you. That's good. Yeah. Even, I mean, this is even maybe a silly question because this is everything, it's above the x-axis. That's when you will probably think, but even if I will drop this, even if everything will be below, it's still positive. Please remember, because it's the total area. It's not the direct integral, it's the application of the definite integral. Definitely positive, but we can leave it for now. You can probably, I think next week you will be so happy because I can show you how quickly we can get the answer. Not like estimating, we have really like pretty nice tools. Okay, and I think we have one more section, but I think I need 5 more minutes, okay? That we do have a section 5.4. Oh, I wanted to circle. Okay, I wanted to circle 5.4, but I think, oh, I can't write so high. That's what we have to know. We have to know how to make the interpretation of a definite integral. You know the symbol, you know the notation, you know the meaning, you know how to calculate from the graph, from the application, from the table. Now we have just to know how to like make the description, the interpretation. Yeah, I think I took an example from your textbook. That means, let's see. If R of t represents the rate at which the heart is pumping the blood in liters per second, and t is time in seconds. Yeah, of course, liters per second. That means now we have to give the units and the meaning of this integral. Integral from 0 to 10 R of t dt. That means we know that this integral will represent the total amount. If this is rate, okay, that means if this, the function is rate, like we remember the velocity, then always, if this is the rate of change of something, then the whole integral will represent the total amount. I can just box this, total amount of the blood. And of course, the unit for the amount, liters, pumped in by the heart between 0 and 10. Okay? That means please remember, like overall is, if the function provided is the rate of change of the quality, then the integral will be total change in quantity between A and B. Okay? Total change. Okay, and then I can skip this. Okay, that means now we can see we do have an definite integral from 1 to 3 Vt dt, where Vt is the velocity in meters per second. That means if this is the velocity, that's what we did start with, what this integral represents. We remember the total distance traveled between 0 and 3. That means, oh, the change in the position, of course. Yeah, the change in the position. Okay, that's the whole integral between 1 and 3. Okay, and then, okay, the acceleration. If the acceleration is placed in, that means the A of t is the acceleration. Acceleration is the rate of change of the velocity with respect to time. Okay? That means if this is the definite integral of the acceleration will represent the change in the velocity. I can write this. Change in velocity. Of course, between 0 and 6 hours. Okay, and the velocity will be measured in, we always losing like, yes, the 1 unit in the denominator. That means this will be kilometers per hour, which of course is obvious, not the hours squared. Okay, that means that's actually all of my questions, okay, for today. That means I'm really hoping you got the understanding of the definite integral from different perspectives, different angles. Okay? From the graph, from the table, from the application, and we understand the net area and one of the application, the area between two curves, always positive. Yes, but not the definite integral. Definite integral could be negative. I can actually put it in. Okay, that means again, thank you very much, and thank you for answering my questions. I'm always really happy to have participants and have people answering my questions. Okay, and you will see me again next week. And good luck with your assignments this week. Please use the discussion board for some additional questions. Okay, thank you.